Okay, so object allocation. So first of all, I'm going to make it allocate a new object, just like I showed you when I sent the first request to the web server, that is in my VMware. Then I make the application deallocate this object, as I showed you with sending three more requests to the web server. Then I override the object. So I'm not. The next section is dedicated to this subject, so I'm not going to tell you now exactly how can I override the same location exactly. And we're going to talk about the content that I'm going to put in it right now. But it usually happens, in order for you to understand it, when I found another place in the application where it allocates buffer of the same size of the size that the object used to be. Okay, so we have two parts to the new content that we insert instead of the old object. The first part is the shellcode. We just insert the shellcode there because we need to insert it someplace. This is the code that we want the application to execute. This is our code, our malicious code that we would like the application to execute and therefore enable us to take over the vulnerable machine. And the second part is our fake virtual function table pointer. We're going to put a new virtual function table pointer instead of the old one. So, as I told you, ECX usually points to the beginning of the object when the application uses objects. Wouldn't it be nice if we could find a way for the application to execute call or jump ECX, and by that make it jump to the beginning of the buffer and execute our shellcode? So I'm going to show you how to do that. First of all, we need to find a place in the memory that has call or jump ECX. Each one of these assembly lines consists of 2 bytes. There is a really good chance that we can find lots of this instruction randomly inside the application memory, and we just need to use one of these locations. We need to use a location that for it I can also find a pointer that points to this location. So this is a difficult task to do, because what are the chances that you're just going to randomly have a pointer that points to another location inside the memory? But this is possible because we have so many call or jump ECX that enables us to just find another. One of them has another location that points to this memory address. So after we found a pointer that points to the call or jump ECX, we just take the address of this pointer, subtract it by 8, and put it in the virtual function table pointer. This will be our new virtual function table pointer, and this will enable us to make the application think that the third virtual function code is actually call or jump ECX. So now when the third virtual function will be executed, as I showed you earlier in the example by shutting down the server, what I did inside the VMware, when it will be executed, it will actually execute my new inserted code and enable me to run my malicious code. So here we have again the code that runs when the function is executed. ECX points to the virtual function table point, to the beginning of the original object. The first assembly line makes EAX point to the beginning of the virtual function table. And then when the application executes call EAX plus 8, it will actually jump to the beginning of our shell code. Yeah, so the question was, I'm actually executing the virtual function table pointer as code, and that's a problem. That's what you meant?
Yes.
Okay. So, usually, I just was about to talk about that. Usually when random bytes are interpreted as code, this is really a problem. But randomly, as I did it, I tried to run many pointer as code when I researched this exploitation technique. I saw that most of random assembly instructions just do not influence dramatically on the execution flow of the application, and it would just execute it and continue to execute my shellcode that just resides afterwards. Okay, so how can we overwrite this object? That's the subject of this section. I'm going to talk a bit about how allocation is implemented, memory allocations are implemented, and deallocations inside Windows applications. So each application has a C runtime heap. This heap is actually part of the memory layout that I talked about earlier. This part of the heap is used to hold data objects that are allocating using the new operator and the malloc function. And actually each allocation that happens with one of the functions that you can see on the slide is performed inside the C runtime heap. Okay, so another thing about allocation implementation is what the application does when it deallocates an object. So the application could return to the operating system each buffer that it deallocates, but that would be inefficient because the application will later want to allocate another buffer of the same size. And it would be inefficient to ask the operating system to provide another buffer of this size. So each application has allocation cache. It saves the deallocated buffers somewhere in the memory, and then when it tries to allocate buffers of the same size, it just takes it from there. So this feature is called a look-aside list. Each application has a different look-aside list for each size between 8 and 1024 in jumps of 8. And so this is the first allocation priority. When the application wants to allocate another object of the same size, the first place it will look in is the look-aside list. So let's see an example and make you understand a bit complicated thing called look-aside list. So this is an example look-aside list. The look-aside list for 40 bytes buffers. So this look-aside list has just one buffer inside it right now. Let's say the application deallocates another buffer in size of 40 bytes. So this is how the look-aside list will look like now. Each item of the look-aside list has in its first dword a pointer to the next buffer of the look-aside list. And the last buffer of the look-aside list has null instead of the pointer. Then that means it points nowhere and that it is the last item of the look-aside list. Let's say this application wants to allocate another buffer of 40 bytes. It will just take the first item of the look-aside list and use it as the buffer it wants to allocate. So whenever an application deallocates a buffer, it inserts it to the beginning of the look-aside list, and whenever it allocates a new buffer, it takes it from the beginning of the look-aside list. Okay, so this is the look-aside list. How is this relevant to the double reference exploit. So this is what we previously did. This is a short review about the double reference exploit that I talked about earlier. I make the application allocate a new buffer using the first request that I sent to the server, to the web server. Now this is just an example. I'm talking about dangling pointers in general, and I'm using this example to illustrate how it is done. So I send the first request and make the application, the IIS application, allocate this buffer. Then I send the three more requests, and I make the IIS server deallocate the buffer. I make the application deallocate the object, and then I have a dangling pointer that points to the object. And between the execution of the virtual function, I override the object, and now I'm going to talk about how it is done. So every big enough application will have many allocations inside it, many execution flows that inside it that result allocations of the buffers of the size that the object used to be. So I just disassemble the code, find these kind of allocations, and another limitation is that I need the newly allocated buffers to have controllable content. I need that as a user I will be able to control the content of these allocation. Now I think that every big enough application, for example the IIS web server, has this kind of, I can find many of these kind of allocations inside it. Now the IIS specifically is a bit complicated because of another thing that I will not get into right now, but I'm going to show you an example for this in the IIS web server. So let me just start the server again. So we're going to start like in the example I showed you earlier. First of all, I browse to the ASPX page. This makes the IIS web server allocate the new object. Then I send 3 requests to this URL. This makes the IIS web server deallocate this object. Now, what I did just now is insert a new configuration item into the IIS configuration. Now, this is not the remote exploit that I talked about. This is just an example of the double reference technique. And this is a local exploit because it requires me to insert a new configuration item into the IIS web server. And the details are in the white paper, so I'm not going to talk about exactly what configuration item or what